Welcome to this lecture on the shortest route problem. Imagine you are trying to drive from your house to a new restaurant across town. You open a navigation app on your phone and it instantly shows you the quickest way to get there. The app evaluates dozens of possible streets, avoiding long detours and traffic jams to give you the absolute best route. Today, we are going to uncover the mathematics behind this everyday scenario. We will learn how to guarantee that no shorter path exists, minimizing effort, time, or distance. To solve this routing problem mathematically, we first need to translate our physical map into a mathematical network, sometimes called a graph. Why does this matter? Because computers cannot read physical maps. They need numbers and connections. A network is made up of nodes and edges. Nodes are the specific points or locations like cities, warehouses, or street intersections. Edges are the lines connecting these nodes, representing the roads, pipes, or pathways between them. Every edge has a weight, which is a number representing the cost to travel that edge, such as miles, minutes, or dollars. Our goal is to find a sequence of connected edges from a starting node to an ending node such that the sum of their weights is as small as possible. Now that we understand the terminology, let us look at a visual representation. The diagram you are seeing shows how a real-world map is simplified into circles and lines. We have 5 nodes, with node 1 as our source and node 5 as our destination. The arrows represent the edges and the numbers next to them are the weights or costs of traveling that specific path. For example, traveling directly from node 1 to node 2 costs 10 units. By assigning a numerical cost to each line, we give our mathematical formulas the exact data they need to compare different routes. The highlighted blue path shows one possible route through the network. With our network defined, how do we actually find the shortest path without checking every single combination, which would take forever? We use a brilliant step-by-step method called Dijkstra's algorithm. Think of this algorithm like a spreading puddle of water, starting from your house. The water flows along the shortest paths first, reaching the closest intersections before the farther ones. It works by dividing all nodes into 2 categories, unlabeled and labeled. An unlabeled node has a distance value that is just our best guess so far. A labeled node has a locked-in distance value. We have mathematically proven that no shorter path to this node exists. We lock in the closest point, look at its neighbors, update their distances if we find a quicker way, and repeat. Now that we know the logic, let us look at the mathematical engine driving it. This formula tells us how to update distances when we lock in a new node. On the left, dj is the new updated distance to our neighbor node j. The min function tells us to choose the smaller of 2 options. The first option is the old dj, which is the best distance we knew before. The second option is di plus cij, which means taking the locked-in shortest path to node I and adding the direct route from I to j. If this new route through I is shorter than the old route, we replace the distance. As the direct cost Cij increases, meaning the road gets longer, it becomes less likely that this new path will be chosen as the minimum. Before we move on, let us see this formula in action with a concrete example. We have a simple 3-node network. The direct road from node 1 to node 2 is 10 miles. The road from node 2 to node 3 is 5 miles. The direct road from node 1 to node 3 is 20 miles. We want to know if it is faster to go directly to node 3 or to take a detour through node 2. We start our algorithm at node 1. The distance from node 1 to itself is obviously 0. We set its distance to 0 and lock it in, making it a permanent label. This is our starting point, and from here, we will look at its neighbors. Continuing with our example, we now look at the neighbors of our locked node 1. First, we update node 2. Its old distance is infinity because we have not visited it yet. The new path is the distance to node 1, which is 0, plus the road from 1 to 2, which is 10. The minimum of infinity and 10 is 10, so node 2 is temporarily labeled as 10 miles away. Next, we update node 3 directly from node 1. Again, the old distance is infinity and the direct road is 20 miles. The minimum is 20. Now we compare our temporary nodes. Node 2 is 10 miles away and node 3 is 20 miles away. Since node 2 is the closest, we lock it in as a permanent label. Now for the final step of this example. We check if going through our newly locked node 2 gives a shortcut to node 3. We apply our formula again. The old best distance to node 3 was 20. The new path is the locked-in distance to node 2, which is 10, plus the road from 2 to 3, which is 5. We compare 20 and 15. Since 15 is less than 20, we update node 3. We have found our final answer. The shortest path from node 1 to node 3 is 15 miles, and we achieve this by traveling through node 2. This perfectly proves that taking a detour can sometimes be shorter than taking a direct route. Dijkstra's algorithm is perfect for a single starting location. But this brings us to a new challenge. What if you are publishing a road atlas and need a massive mileage chart showing the distance between every single pair of cities in the country? Running Dijkstra from every single city would be exhausting and slow. Instead, we use the Floyd-Warshall algorithm. This solves the all pairs shortest path problem. It uses a concept called dynamic programming, which breaks a massive, complex problem down into smaller, simpler, overlapping steps. Think of this like a giant spreadsheet where you are constantly asking one question. If I use city K as a pit stop, does it make the trip between city I and city J shorter? By systematically checking every possible pit stop, we build a perfect chart of all shortest routes. Now that we understand the goal of Floyd-Warshall, let us look at its mathematical heart. This formula updates our distance matrix at each stage k. The term on the left is the new distance we are calculating for the current stage. The min function compares two values. The first is the best distance we had in the previous stage without using node k. The second is the cost of traveling from the start I to the pit stop k plus the cost of traveling from the pit stop k to the destination j. If the detour through k is cheaper, we replace the old distance. As the matrix updates, every value represents the absolute shortest path discovered so far. If the detour cost increases, the algorithm simply keeps the previous best distance. Let us see this dynamic programming formula in action. Imagine a 3-node network. The direct distance from node 1 to node 3 is 50 miles. The distance from node 1 to node 2 is 10 miles, and from node 2 to node 3 is 15 miles. We want to update the distance from node 1 to node 3 using node 2 as an intermediate pit stop. This represents stage k equals 2 of the algorithm. We will apply the Floyd-Warshall formula specifically for starting node 1, ending node 3, and pit stop node 2. We are setting up to compare the direct route we already know against the potential detour through node 2. Continuing with our calculation, we substitute the known distances into the formula. The superscript 1 means we are using the best distances we knew before considering node 2. The old direct path was 50 miles. The path to the pit stop is 10 miles, and from the pit stop to the end is 15 miles. We add the detour distances together to get 25 miles. Now we compare the old route of 50 with the new route of 25. Since 25 is less than 50, the matrix is updated. The new shortest distance from node 1 to node 3 is 25 miles. This shows exactly how the algorithm systematically finds shortcuts and updates the master distance chart. Now that we have used these formulas, let us understand why all this matters in the real world. Without shortest route algorithms, modern life would grind to a halt. Every time you send an email, the data is broken into packets that must find the quickest path through the global network of internet routers. Delivery companies like FedEx and Amazon use these exact mathematical models to route their trucks, saving millions of dollars in fuel and time. Emergency services rely on them to dispatch ambulances along the fastest possible roads. By turning physical maps into mathematical networks, operations research ensures that resources are never wasted on inefficient paths. We have reached the end of our topic. So let us review the key takeaways. First, the shortest route problem is all about finding the most efficient path through a network of connected points. Second, we use Dijkstra's algorithm to find the best paths from a single starting location by locking in distances one by one. Third, when we need a complete map of distances between every possible pair of locations, we use the Floyd-Warshall algorithm to systematically check every possible detour. You have now covered the full topic. Together, these mathematical tools form the invisible backbone of modern navigation and logistics.